Well, folks, I think it is that time again. That's right. It's time for me to draw crude diagrams in Photoshop while talking to myself and failing at typing. I mean, it's time for another lesson in the intermediate game programming tutorial series. If I can find my thingamajig. Why is this an hourglass? It's annoying. Stop that. There. So, like I was saying before, we are working our way towards the framework. I'm teaching you guys the stuff that you're going to need to know to understand how the framework works. There's a few topics left, and today we're going to be doing bit twiddling. That's this one. That was really diagonal. Undo. Control Z. Yes. Okay. Bit twiddling. We'll get to what that means in a little while. These other topics, you might look at this list and say, holy shit, we got a lot of stuff to go. But all four of these topics, we can do them all in a single lesson. So it's not going to be a very practical lesson. It's just going to be me explaining what all this shit is without giving an actual practical example of it. But it'll make the whatchamacallit, the tutorials on the framework a lot easier, a lot smoother if you already know a little bit about these topics before I go into them. I don't want to have to keep pausing to explain shit when I'm explaining the framework. I want to just be able to roll through that mother smooth as X-lax. So lesson 2 is bit twiddling, lesson 3 is this miscellaneous shit, and lesson 4 until maybe lesson 6 will be me teaching you everything that's in the framework. It might only be 2 lessons, it might be 3, but I don't think I'll be able to fit it all into one lesson. I mean, I could. It would just be like a 6-hour lesson or something, but nah, we don't need that shit. So I'll probably split it up. Splitting it up will get lessons out there faster to you guys, so it's always good. Now, bit twiddling. This is the manipulation of bits in a word or in a number, a value, right? Values in basically any kind of computer, most computers, are represented as binary numbers, bits. And bit twiddling, bit manipulation, that will let us work on these individual bits. So most of the operators that we've come across so far, they work on entire numbers as a single value. And these operators that I'm going to be teaching you are going to work on the individual bits in a single value. That might not make sense right now, but don't worry, it will eventually. Now, the good news is that I have a perfect topic that will go hand in hand with this bit twiddling. And that perfect topic is the actual practical topic of today's lesson, which is alpha blending. So alpha blending, well, most implementations generally require you to do some bit twiddling. So we can kill 2 birds with 1 stone. We can learn a new graphic technique while we learn a new programming topic. And we'll learn some math theory. So we'll get a trifecta of just shit that you'll learn in this lesson. And because we're going to get this trifecta, this lesson is probably going to be another long-ish one. Maybe over 2 hours. Under 3 hours. We'll see. We'll see what we're going to get there. So, let's get started. First of all, for those of you who have no idea what alpha blending is, I got a little demonstration for you. So I've got 2 layers right here visible. Let me just show you. I've got this layer, which is just me doodling on a transparent background here. And then I've got this layer, let me just show you, which is just a blue, right? The blue is over top of the doodle. Now, Because the blue is sitting over top of that doodle, it overwrites it and you can't see the doodles unless you turn down the opacity. So if you make it, what's the word I'm looking for? Translucent, then you can see through it and you get a kind of blending of what's below and what's above. And that, my friends, is alpha blending. You start off with this image here of the squiggles, and then over top of it you blend in, well, in this case it's just a blue, so you're blending the blue in there. Now how that works is what we call a weighted sum. So for every pixel, you're going to have a source pixel, and you're going to have a destination pixel. Let's look at this again. So here are the destination. This is the destination pixels. This is what is already sitting on the screen. So these lines here, they're all part of the destination. So if we take this point here, the destination pixel would be some kind of gray color, right? Now the source, what's going to be drawn over top of that, is blue, because everything in this color is blue. And what we're going to do is we're going to have some operation to blend the source and destination and give us a final result pixel. And how we do that is we do something called a weighted sum. I think I might have said that already. Weighted sum. W-E-I-G-H-T-E-D sum. There. So what the fuck is that? Well, I'll give you an example. The easiest example of a weighted sum, the example that everyone should be familiar with, is an average, right? So if you take the average of two numbers, like let's say 7 and 5, what you do is you take 7 and you multiply it by 0.5. And you multiply 5 by 0.5 and you add them together. And you're going to get the average, which better be 6. That is a weighted sum where both of the arguments are equally weighted. They're both given equal weight. But you can also have a weighted sum where they're not given equal weight. So for example, if you had 7 times 0.1 plus 5 times 0.9, you would be favoring the 5. So your number here, this weighted sum, would probably give you a number closer to 5, like 5 point, I don't know, 2 or something like that. I have no idea actually. I'm going to say 5.2 just because I like to guess. But yeah. So in that case, you're taking more of this value, and you're taking only a little bit of this one to make up the final value. And what we do when we're doing alpha blending is we break the color down into its RGB values, right? RGB. So if this is the source and this is the destination, here we have R source, G source, B source, and here we have R destination, G destination, B destination. And what you're going to do is you're going to multiply it by some weight. So we'll call this one weight 1, weight 1. And here we have weight 2, weight 2, weight 2. And we add them together. And the result, RR, GR, BR, is the final pixel that we're going to have on the screen. It's just a weighted sum between the components of the colors. Now, for reasons which I have no idea of, we call the weights, we call them the alpha values. So we have alpha, alpha, alpha. So you can have alpha 1, and here we have alpha 2. But the thing is that alpha 1 plus alpha 2 has to equal 1. The reason why it has to equal 1 is because if you make it less than 1, your colors are going to get darker. So you could try to alpha blend white with white, but if your alpha 1 plus alpha 2 is less than 1, your result will be like a gray color. And likewise, if alpha 1 plus alpha 2 is more than 1, your colors are going to be brighter than what would be like an average of the two or whatever. So you'll get an amplification if your alphas add up to more than 1, and you'll get an attenuation if your alphas add up to less than 1. So if you want to blend them without actually amplifying them or making them smaller, your alphas have to add up to 1. So what we normally do is we say, instead of alpha 1 and alpha 2, we just say the source is multiplied by alpha, and the destination is multiplied by 1 minus alpha, 1 minus alpha, 1 minus alpha. And of course, alpha plus 1 minus alpha is equal to 1, right? So that'll always add up to 1. Or in other words, we multiply the source by alpha, and we multiply the destination by the inverse of alpha, or the complement of alpha, whatever the fuck you want to call it. Anyways, that's alpha, and that's why we call it alpha blending, because we generally call the weight that we use for the blending, we call it alpha. Okay, so this is how we calculate our final pixel values. Now the problem comes in, our D3D color is a 32-bit value which contains the R, G, and B inside of it. And in order to do this, we have to separate the R, G, and B's out into separate variables so that we can blend them. And then we have to put them back together. Now we have a function to put them back together. It's I think it's D3D color underscore XRGB, right? This, well, it's not a function actually, it's a macro, but same idea. We can use this to take 3 separate values and make one 32-bit D3D color value. But we don't have any functions to extract the red, the green, and the blue from a D3D color. So we'll have to make those. And in order to make those, we need bit twiddling, and we need to understand how binary numbers work. Binary numbers. So we need to understand binary, and we need to understand bit manipulation, bit shifting, and bit logic. So, how to do this? I think first I'm gonna turn this background off. Where's my put the pen on the pen tablet, and then you can't move your mouse. Alright, what am I gonna do here? I want to take this layer and I'm gonna make it white. Bam. Then I'm gonna draw on this layer. Okay, so let's learn about binary numbers. This is the theoretical math part of this lesson. Now, there are many ways to represent a single number. But it would help if I was drawing in black instead of in white. So let's say we have the number 7. We got 7 things here. 1, 2, 3, 4, 5, 6, 7, right? How to represent that? Well, most of us would probably represent it like this, with the digit 7, right? We have symbols 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 10 symbols that we use to represent numbers. So we count this, we go 1, 2, 3, 4, 5, 6, 7. So we count here. 1, 2, 3, 4, 5, 6, 7. And we use this symbol to represent this amount of things, right? Now, what if we were to add more shit? Well, if we had 9 things, we would write a 9. Now, if I add one more thing, I can't represent this amount with a single symbol, because our symbols, we only have 10 symbols, 0 through 9. So what I do is I go over a space here. I add a new digit. And now I say that this digit here is worth more than this digit here. It's 10 times more, actually. So we take the face value of this digit, which is 1, and we multiply it by 10. Here we multiply the face value of this digit by 1, which is just itself. And here, this one's worth 100, right? 1,000, and so forth. And this is how numbers work, right? This one is called the decimal system because deci, or dec, I think dec means like 10. And we have 10 symbols to work with. And because we have 10 symbols, the values of our digits, our number places, they go up by 10 every time, by a factor of 10. Now, one theory why this system is popular is because we have 10 fingers, so we use counting, we count with 10. But I think it was the Sumerians or the Babylonians, maybe, I'm not sure. But they used base 60. So they had 60 different symbols for any given place. And by the way, that's the reason why we have 60 seconds in a minute and 60 minutes in an hour. That comes way back from the whoever, the Babylonians or the Sumerians. I'm not sure who made up that crazy shit, but it's from way back when. Now, base 60, we're not gonna be talking about that. Oh yeah, decimal is also known as base 10 because, again, 10 symbols and the values of places go up by 10 every time. Now here's the thing. Computers don't have 10 fingers and 10 toes. It doesn't make sense for them to work in base 10. Computers run on electricity, and it just so happens that when we're making electric circuits, the easiest way to represent data is either by power on or power off. On or off. Or high voltage, low voltage, or high current, low current. It's generally easy to represent things with two different states, high or low. And so that gives us only two symbols. So if we wanted to put a picture to these symbols, we could use 1 and 0 to represent high and low. We could use 0 to represent low, and we could use 1 to represent high. It doesn't matter, but generally that's the way we do it. So how would that work? Well, if we were counting 0 things, we could write our number as 0. That's the same as in decimal. If we had 0 things, we would write it in 0. Let me just let me make a column here. Fucker. I'm getting dyslexic now. Decimal. Here, binary. Binary is this system here with only 2 states. We call it binary. Why? Bi means 2. Des don't think I'm missing a C there. Dec means 10, right? So this is base 10, base 2. Okay. So 0 things, that would be 0 in decimal and 0 in binary. 1 thing, that's 1 and 1 in binary. 2 things, well, that's 2 in decimal. However, in binary, we don't have a symbol for 2. We're out of symbols. So what did we do in decimal when we were out of symbols? We went over one place. So this is the situation in binary for 2. This is 2 in binary. Here's 3. All right. Here's 1, 2, 3, 4, 5, 6. Decimal, we got 6. And in binary, 6 is, this is 2. This is 4 plus 2 is 6. Right? Notice in decimal we go like this. We go, the first decimal place is worth 1, then it's worth 10, 100, 1000. In binary, the first place is worth 1, the second is worth 2, then 4, then 8, and so forth. We're going up by powers of 2. Times 2, times 2, times 2, times 10, times 10, times 10. Base 2, base 10. Alright. And so we got 6 here, 7, 8 would be like this. And 10, now we've gotten into a new digit in our binary, or in our decimal here. And 10 would be 8 plus 2. So here's the binary, here's the decimal. Let me think here. Put my pen back on my tablet. Now, most computer systems, they don't allow you to access individual bits directly in memory. The smallest amount of data you can access is a byte. A byte is 8 bits. By the way, a bit means binary digit, bit. Now, a byte is 8 bits. So that's 8 binary digits, right? So if we got 1, 2, 3, 4, 5, 6, 7, 8. And if we turn them all to 1, that's the biggest number you can get in 8 bits, or a single byte, which is 255. And if you'll remember, 255 is the largest number that we could specify for our colors, because every color channel is 8 bits, or a single byte. So that's why in our colors we could only specify from 0 to 255. If we specified 256, 256 is this number here. 0, 0, 0, 0. And when we try to move 256 into a single byte value, it'll only take this part, which means it'll look like 0 when we try to pass that to the put pixel function. So just a little bit of trivia for you there. Now, we can add binary numbers the same as we add in decimal. Let's say we were going to add a... let's think here. Let's try and add these two binary numbers. These numbers, by the way, are 7 and 6. So that's 7 plus 6. So to add them in binary, we go 0 plus 1 is 1. 1 plus 1 is 0, carry the 1. And here we have 1 We're carrying the 1, so we got to put it here. 1 plus 1 plus 1 is 1, carry the 1. And this number, by the way, is 8 plus 4, which is 12, plus 1, which is 13. And we know that 7 plus 6 is 13. So that works fine. We could also subtract numbers. If we wanted to do 100 minus 011, we try to subtract here. Can't do it. So we'd borrow from here. 10 minus 1 is 1. And here we have 1 minus 1 is 0. And here 0 minus 0 is 0. So here we have 8. No, we have 4 minus 3 is 1. And 100 minus 011 is 001. So we can do arithmetic like this in binary. Now the trick is, I'm just going to go into this very shortly, not going in depth, but when we were writing just on a piece of paper and we want to show a negative number, we go something like -3. But in a computer, there is no way to show a negative symbol. There's only bits. So in an 8-bit number, there's only 8 bits. So how do you show that a number is negative or positive? The way you show it is, there's a number of ways you could try to do it. One, the simplest way is to say, okay, you have an 8-bit number here. Bam, 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 bam. And we could just say that this bit here is the sign bit. So if it's 0, that means the number is positive, and if it's 1, the number is negative. And these bits here are the value bits. So that would give us a possibility of, in 8 bits, we could have a number which goes from plus 127 to minus 127. But, and this is simple to look at, to understand, but it's not the best way of representing negative numbers in binary. One reason why it's not the best way is look at the number for 0, right? 0, 0, 0, 0, 0, 0, 0, 0, this would give us 0. But 1, 0, 0, 0, 0, 0, 0, 0 will also give us 0, right? This is positive 0 and this is negative 0. You don't need 2 different ways of representing 0. It seems like a waste, first of all. Second of all, if you use this representation, your math is not going to work out properly. It's going to be more difficult to make circuits to add things. Let me show you an example. So let's say we're going to add 2 numbers together. We're going to add a negative number. This is -3. And we're going to add this one to positive 2. So this is -3 plus positive 2. -3 plus 2. The answer should be -1. But if we add these 2 numbers together, 1, 0, 0, using our normal just procedure, 0, we're going to carry this one, so this is going to be 1, 0, 1. And the answer here would be what is it, 6 plus 1 is 7. Seems wrong. 4, 5, right? 4 plus 1, 5. There. Which is totally wrong, right? So we can't use our normal adding procedure if we choose this representation. the very simple representation of the top bit reserved for indicating sign. So, what other way could we represent numbers? Now, I'm only going to touch on this very lightly because it's kind of complicated and I'm not sure it'll be that useful. But for completeness sake, I'm going to cover it very shortly. If you don't understand it, that's fine. If you don't understand it but you want to understand it, you can look this shit up on the internet. There's tons of tutorials on this stuff, binary representations. So just as a simple explanation, I'm going to show you how the numbers are represented, positive and negative numbers are represented actually in most computer systems. Now what we do is we use what's called the 2's complement. I think that's the right way of spelling it. 2's complement. Now 2's complement, for positive numbers, it works exactly the same as just unsigned numbers. 2's complement, it also uses the top bit as a sign bit. So if the top bit is 0, that means the number is positive. So for example, this number here is fucker. It's not fucker, I can't write properly. This number here is 127. Positive 127. Right? Okay? Now it uses negative numbers, they have this bit turned on. So that's the same as our previous implementation, but it's a little different. This number here is -1. So if you turn all the bits on, you get the smallest negative number possible. Now if you turn all the bits off except for the sign bit, you get -128. So that's the highest magnitude of negative number you can get. Now note that the highest magnitude of positive number and the highest magnitude of negative number is different. And that's because, unlike the other one, there's only one way to represent 0. So the positive numbers really go from 0 to 127, and the negative numbers go from -1 to -128. So you don't get that duplication of 0. That's the first good thing about this representation. The second good thing is that if you add the numbers together, you get the expected result. So, let me think here. Well, let's try and add 0, 0, 0, 0, 0, 0. No. We're going to try to add +3 plus now I've got to remember how to figure out -2. It's tricky. This is -1, so I'm thinking this is -2. Add. So +3 plus -2 should equal to +1, right? Let's add them together. We get a 1 here. Now we add these two, we get a 0, carry the 1. Add these two, 0, carry the 1. Add these two, 0, carry the 1. 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 But this 1 is outside of our 8-bit range, so it just gets ignored. The answer, 0, 0, 0, 0, 0, 0, 1. Alright? Which is the correct answer. So you can see here, if we use this representation, the 2's complement representation for our negative numbers, we get a result which is consistent with normal mathematics. Now, why do they call it the 2's complement? Well, that comes from the way that you find the negative number. If you want to find a 2's complement negative number, you subtract it from... it's hard to explain. Hard for me to explain it. But let's say you wanted to find the negative value for it's going to be hard to do. Okay, let's say we're not going to be working in 8-bit numbers right now. We're going to work in 4-bit. There were computers and lots of calculators that worked in 4-bit. So it's something that has happened in the past, and it's a lot easier to do on pen and paper than 8-bit. So if we have a 4-bit number and we use signed representation, positive and negative, the largest number we can get, the most positive number, is 7, and the most negative number we can get is -8. Okay? So that's 4-bit signed. Now, how do I find a negative representation? Well, what we do is we take the positive representation. Let's say I wanted to find -7. I would take +7 and I would subtract that from this value, which is 8. No, 16. Right. Well, 16 unsigned, but anyways, you subtract it from this one. So you take the you put full zeros for the size of the word, and then you add a 1 to the end, basically. And if I subtract this from this using normal math, so subtracting this would give me 1, 1, 1, and 1 0 over here. Subtract this from this, we get a 1. Subtract this from this, we get 0, 0, and 0 minus 1 minus 0 is this. So this is the representation of -7 in 4-bit signed. And that's how you find it. You subtract the positive representation from this value, which is 1 over the largest represented value. It's hard to explain in words, but if you look at it. I'm not good at explaining this stuff. So pictures speaks louder than words, whatever. It's worth 1 billion words. One picture, one poorly, crudely drawn diagram is worth 1 billion of Chili's words. So that is how you find it. And it's interesting. One last thing I want to show you, which is something that's often drawn, is a number wheel. So if we say that, let's draw a number wheel for a 4-bit signed number. I need more space. I need lots more space. I need a bigger eraser. But I'm too lazy to change my eraser size. Because that's how I roll. Lazy. I could just do something else, like I don't know. I could draw a big white rectangle and erase the whole thing. I could pause the video, but I'm almost done erasing, so it would probably just be a waste. Plus, I think pausing the video introduces like some kind of desynchronization between the audio and the video, which always pisses me off. Okay, so now we're going to draw a number wheel. So I'm going to try to draw a circle and not fail at it. Good enough-ish. Yeah, that's circle. Misshapen potato that it is. Now, at the top we will draw, let me think here. 0, 0, 0, 0. Okay, I'm going to draw 0 here. Halfway between 0 and what is what? What should this be? 0 here, and this will be positive 7. Now here will be negative 1. What should be over here? I'm thinking this should be 3. 1, 2, 3, 4. 1, 2, 3, 4. Should be 4, 5, 6. 1, 2, 3. This will be negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8. Yeah, that's kind of messed up, but it's close enough, I think. 4, 5, 5, 6, 6, 7, 7, 8. So if we count how many symbols we have here, we should have 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Because a 16-bit number can represent a total of 16 different combinations in binary. A 4-bit number can give us 16 different combinations. So here we have 0, 0, 0, 1, 0, 0, 0. Fuck it. 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1. Fuck! Fuck me! This is the Tourette's syndrome part of the lesson, by the way. As if there were any other kind of part to my lessons. And 0, 1, 1, 1. Right? Here's all the positive numbers. Now if we move over to the negative, 1, 0, 0, 0. Fuck! See, notice when we get to this point, we roll over from the biggest positive number to the biggest negative number. This is called overflow. Or I think this is called an overflow inside numbers. Yeah. But it's interesting to note that we can use our same pattern of counting up in binary to count down in signed notation. 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. There you go. So here's our number wheel in binary. And the way our number wheel works is we can move in this direction from here to here with no problems. And we can move in this direction from here to here with no problems. But if we try to, for example, if we try to add 1 to 7, we try to cross, there's a line right here. And if we try to cross this line by adding 1 to 7 or subtracting 1 from 8, we'll get an overflow or an underflow, and we'll fuck up our number system. But this is how the number wheel works for 4-bit binary signed 4-bit binary. And yeah, I'm not going to explain signed numbers any more than that. That's as much as I'm going to explain those numbers, because it's not that important really, I don't think. But it's always nice to know a little bit about how these things work. And that is also why we have in C++, in C, we have the unsigned specifier when we're declaring an integer or a character. And what unsigned means, unsigned int, that means don't think about signed bits, just do whatever. Well, I don't want to use int because it's too big. I don't want to draw that many things. But if we do unsigned char, that means 11111111 is equal to 255. Whereas if we don't put unsigned, we just do char, in that case 11111111 equals negative 128. Right? It's just how we're looking at the bits in memory. But yeah, and there's other things too, like signed numbers. When you multiply them, you have to there's different calculations. It all happens inside the CPU. There are different machine instructions for signed and unsigned multiplication and division, but addition is the same for signed and unsigned. Mostly it's the same, and the reason why is because I showed you the number wheel. It works out very nicely. So that is binary numbers. Now I'm going to tell you guys one more thing. So we have decimal, which has 10 symbols, and we have binary, which has 2 symbols. Yeah. 2 base name. But we also have hexadecimal, which has 16 symbols. Now, why would you want to have 16 symbols? First of all, what the fuck? How are you going to get 16 symbols? We only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 symbols if we count the 0, which we do. How are you going to write a number with 16 symbols? Well, you just go A, B, C, D, E, F, and you're all set, right? Now you got 16 symbols. The question is, why would you want 16 symbols? Well, 16 is 2 to the power 4, right? So if you have a 4-bit binary number, like 1111, that's represented as F in hexadecimal. So if you max out all 4 symbols in a binary, this 4 bits, by the way, is often referred to as a nibble. Very cute, right? 8 bits is a byte, 4 bits is a nibble. If you max out a 4-bit number, that's the same as maxing out a single-digit hex number. So 1 hex digit exactly corresponds to 4 binary digits, or 4 bits. Whereas with decimal, 1 hex digit, or 4 binary digits is 15, right? This is totally not maxing out these 2 digits here. So it's kind of half-assed. The representation between decimal and binary is half-assed, because 10, you can't go 2 to the power of n equals 10, because n would be like some fucked up number. I don't know, like 2 to the power of 3 point something is equal to 10. It's not a nice even thing. But with hexadecimal, 2 to the power of 4 is 16. And so hexadecimal represents binary very nicely. And that's why we have binary, because people don't want to sit there fucking writing 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 1, 0, 0 or something. That's a fucking pain in the ass. It's much easier to be able to write like 1F, 2A or something like that. This is a 16-bit number, right? A byte is just 2 hexadecimal digits, right? A 16-bit number, which, by the way, 16-bit numbers are often referred to as a word in x86 or in Windows. I'm not going to explain why, because I don't want to talk that much. But 16-bit is often a word. 32-bit is often referred to as a D word, which is a double word. 64-bit is a Q word. Let me just write this in here. 32 is a D word, 64 is a Q word, and 128 is a DQ word, a double quad word. Quad word, double word, word, 8 bits is a byte, and sometimes if we're working with 4 bits, not very often, but if it happens, we call it a nibble. Sometimes. Right. So, what was I talking about? Oh yeah, hexadecimal, very useful for representing binary numbers by... it's a shorthand for binary is what it is. It saves us the trouble of typing ones and zeros for fucking ever. We'll just wear out our keyboard. Like all the one and the zero key will all be fucked up, and the rest of the keys will be fine, and it'll be a badass situation. We gotta spread out the load. That's what I'm saying. So that's a hexadecimal for you. And it's base 16, so obviously the number 16 this is 16, and this is 32, and this is 32 plus 15, which is 47. Yes. Yeah, I'm good at maths. 2f is equal to 47. I could be lying to you. I mean, I don't know. Let's get our programmer calculator out. 47, and we'll convert that to hexadecimal. 2f. Fuck, I'm good. Look, here, I wasn't lying to you. Quad word. This is a Q word. Double word, 32 bits. Word, 16 bits. Byte, 8 bits. That's how you know it's a programmer's calculator, because it's got all this shit in it. Now, I should use that more often. I should have fucking used that before. It's much prettier than my handwriting. Anyways, so that's the gist of binary numbers. Now, there are special operators which work on binary numbers. They don't work on... like, for example, you could take a binary number like 7 and this number, and you could add them together, and that's taking the entire number represented by these 4 bits and adding it to the entire number represented by these bits. But there's also operations that don't consider the bits together as an entire number. Instead, they consider the bits separately. So if I had this number here, there's operations which only work on these bits together. So it only considers this bit and this bit, this one and this one, this one and this one, and it gives us a result like that. It doesn't consider them as entire numbers. It doesn't fucking care about the other bits. It just cares about, look at the first bit in the first number and the first bit in the second number and do something to them and get a result. And do the same for the second bits, third bits, fourth bits. These are called bitwise operators. And they just look at the bits. They don't look at the numbers as a whole. So what are the bitwise operators? Well, you'll be happy to know that they are familiar logic operators. Remember our Boolean AND and our Boolean OR? So we would have a value on the left, which is either true or false, and a value on the right, which is either true or false. And this whole thing would resolve to true or false, depending on the value on the left and the value on the right, right? So L, R, and result, which is small r, because I can't fucking think of anything else. So I'm going to use R twice, and just fucking deal with it. So, if they're both false, the result is false. True, false, the result is false. False, true, the result is false. True, true, the result is true. So what AND is saying is that they both have to be true for the result to be true. Shut up! God damn it. 1 second. Fuck. Shut up! Okay, thank you. Okay, what was I talking about now? Oh yeah, OR. Just a quick recap here again. L, R, and result. So if it's false, false, the result is false. If it's false, true, the result is true. True, true, true. Wait. True, false, true. True, true, true. So what OR means, this is AND, this is OR. And what OR is saying is that if either the left or the right are true, At least one of them has to be true. If any one of them is true, then the whole thing is true. If they're both true, it's still true. But if they're both false, then, sorry, it's false, right? Whereas AND says that they both have to be true. These are the true Boolean operators that we've used. And the other Boolean operator is, of course, the unary operator. It only takes one value, and it's the not operator, right? And what it says is, let me just put it here, if the, I don't know, V for value and R for result. If the value is true, the result is false. If the value is false, the result is true. Right? It just gives us the opposite. That's the not. It inverts the truth. So we have our AND, our OR, and our NOT. And we can also do these with the bits in our values. So let's take a 4-bit number, 1100. And let's take another 4-bit value, 1010. And let's do an AND operation. And all we do is we go 0, 0. 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is 1. Here's the bitwise AND. Likewise, the bitwise OR, which is kind of awkward because it looks like a fucking 1, but whatever, of these two would be, this is an OR, by the way. It's not a 1, it's an OR. 0 or 0, 0. 0 or 1, 1. 1 or 0, 1. 1 or 1, 1. Bitwise AND, bitwise OR. Or we could take the bitwise NOT. This is the bitwise NOT, by the way. The bitwise NOT of 1100 is 0011. And these are the operators, the bitwise operators for C. So we could take two values, like for example, we could say car A is equal to 8. And car B is equal to 7. Okay? And if we did A and B, the answer would be 0. Do you know why? Well, what's 8 in binary? 8 is this number here. 0, 0, 0. This is 8. What's 7? 7 is this. 0, 0, 0, 0, 0. We take the AND. 0 and 1, 0, 0, 0. Eight is this. This is 8. 0, 1 and 0, 0, 0, 0, 0, 0, right? Likewise, A or B. Notice that bitwise OR is different than logical OR. Logical OR has 2, bitwise OR has only 1 thing here. This gives us a Boolean result. This gives us just a number, just a binary number. So, A or B, well, let's look at this. OR is 1, 1, 1, 1, and these are all zeros. The result? 15. So that is bitwise operators. Okay. Now, the thing is, why is this useful? That's the question. How can this ever be helpful to anyone, anywhere, anytime? I'm going to explain that to you, but first I'm going to explain to you one more type of operator. These are the bitwise binary logic operators. Bitwise binary logic. We also have the binary shift operators. And they are very simple to understand. Let's say I have a binary number like this. and I shift it to the left, this is left shift operator, by 2 digits, the result, this. If I have this number here, well, let's say I'm working only in 4-bit binary here, 4-bit, and I shift this one left by 2, or if I shift it by 3 left, the result will be 1 0 0 0, right? These bits will be shifted out and will be lost, and the result will be this. I can also shift right, so if I had the number 8 and I shifted it right by 2, the result would be 2. That's the result. Result, result. So I can shift right or I can shift left. Shifting left generally makes a number bigger, unless you shift out some bits and you lose them. Shifting right generally makes a number smaller. Now, how would that help someone? Well, it's easy to see one way where shifting can help you out. Look at a decimal number, just for shits and giggles. Look at the number 4. Let's shift 4 by 1 in decimal. Well, the result would be 40. We're shifting the digit 4 left by 1. Now, what is the relationship between these two numbers? Well, 4 is 10 times smaller than 40. Shifting it left by 1 multiplied it by 10. Alright, now let's look at a binary number, 0001, and let's shift it left by 1. The result, 0010. This number is 1, this number is 2. We just multiplied it by 2. How do you know? Well, let's try shifting it left by 2 now. Shift this digit over by 2. The result is 4. So shifting it left by 2 multiplies by 4. Shifting it left by 3 multiplies it by 8. So, can you get the relationship? I hope you can. Shifting left by n, so let's say we do A, shifted left by n. This is the same as saying A times 2 to the power of n. So if we're shifting left by 3, 2 to the power of 3 is 8, so it's A times 8. And likewise, if we shift right, we can divide by powers of 2. And I actually do this in the framework in one place. This used to be a very common way of optimizing algorithms. It used to be that multiplication and division was excruciatingly slow on Intel processors. And one way you could speed it up was by avoiding multiplication and just using bit shifting. You could shift left to multiply by powers of 2, and you could shift right to divide by powers of 2. And using bit shifting, you could speed up your programs a lot, your calculations. These days, it's not that big of a deal because multiplication is pretty damn fast. You can still get a little bit of a speed up, but it's usually not worth it. And it makes your programs harder to read and harder to maintain. But that's one way of using bit shifting. It's a way of doing multiplication and division without doing multiplication or division. Right, I'll just give you one last example. This is the value 3, right? And if I shift it left by 1, I get this value, which is 4 plus 2, 6, right? So again, shifting it left by 1 multiplies by 2. Shifting left again by 1 multiplies it by 2 again, which is end result multiplied by 4. Okay, now, back to my earlier question of how does this and or, how does this shit help us out anyways? Using and, using or, and using bit shifting, how can we use that? Well, I can give you a good example of why we need to use and or. And how I'm going to give that example is by going back to our problem of alpha blending. Oh man. Dude, I could go back to alpha blending, but fuck, I paused the video and I can't remember where I paused it. Anyways, before we get to the problem of alpha blending, I just want to quickly show you guys how this works in code. So we're gonna do a quick little console application here. I'm gonna go new project. We're gonna go console application Win32. We need a name. I'm gonna call it Bit Twiddler EX. And we go to application settings. We get rid of that evil precompiled header, and we make our project empty. 'Cause that's how we roll. And then we go project, add new item, C++ file, main. And then we go #include stdio.h, and we go void main. A lot of people say void main is evil. Like that's not, it's actually not standard, and it's probably bad, but I'm gonna fucking do it anyways. If you got a problem with that, you can suck my balls. Okay, now let's quickly show you what I was doing before. So let's go car. We could do unsigned car, but I don't care. I'm just gonna do car. A is equal to 7. Car B is equal to 8. Print F %d \n, and we'll just give the value of A and B, bitwise and we'll copy that, and we'll do A or B. There. And we can see A and B is 0, A or B is 15. I don't know what else I want to really show you guys. We could do we could shift A, which is 7. We could shift that to the left by 1. And that should give us 7 times 2, which is 14. Right? Yes. And that is 14. There we go. Now if we shift it right twice, we'll get 7 times 4, which is 28. Here we got 28. I could go into debug mode here. And fuck. I can't show binary display. This one doesn't show binary because, well, it's just not that good to look at. It's not pretty. What else could I do? I could go car C is equal to what? A shifted left 3 times. Now, printf also lets us display our variables in hexadecimal. If we put, instead of putting %d for decimal, if we put %x for hexadecimal, it'll display the numbers in hex. So I'm going to display C in hex. Fucker. And now I'm going to display it in decimal. I'm going to give you both of those. That'll be the last 2 numbers. So here we have 38. That's the hexadecimal equivalent of 56. Right. So A shifted left 3 times is 56, and if we put that in hex, that's 38. Right, so that was what, 50, no wait, that was 38. So if I add, no, that's the wrong one. If I go 38 plus 2, that should then give me 3A. Yeah, 3A, hexadecimal. What else? Well, I could show you guys what happens when you get an overflow. So these characters are signed characters. So if I shift left too many times, what'll happen is I'll shift one bit into the sign bit, and it'll totally flip the number around. So let's see what happens when I go %sign D. A shifted left. Okay, I have to shift it left 5 times, I think, to fuck up the number. Wait, 224. That's interesting. It's not interpreting these numbers as a single character. It's promoting it to a larger value. If I say, nope, this is a character, then I'll get -32. Alright. It promotes, when I shift it 5 over, it'll promote it to the biggest value, like an int or whatever. So I have to actually specify, no, this is a character, so... Right. And then it'll treat it like a character, and it'll say, well, you shifted it that far over, so it becomes negative. Alright. Well, anyways, that's how this shit works. Don't get them mixed up with this operator or this one, because that gives you different values. Right, that'll just give you 1 and 1, because that's just a logical equivalent. Boolean, so it'll only give you 1 or a 0. Alright. Now that I've gotten that out of the way, we can get back to the topic at hand, which is this shit, alpha blending. Now, here's the deal. Could not use the eraser because the target layer is hidden. Suck on my balls. Now, I'm not exactly 100% sure. I should probably look it up just to be sure, but I'm not going to. I'm going to assume. Now, we have a 32-bit value here. So in hexadecimal, there's the top 8 bits, the next 8, the next 8, and the next 8. This is hexadecimal notation for a 32-bit value, which is 0. Now, our D3D color is 32 bits. And it's broken down into the top 8 bits are unused. And here we have R, G, and B, RGB. So if we had, for example, a white pixel, that pixel's value would be 00, FF, FF, FF. And a green pixel would be 00, 00, FF, 00. Okay? That's white, green. All right? Are you with me so far? Now the trick is, how do we isolate these 3 channels? Right now they're all jammed together in one 32-bit number. How do we extract the separate channels out into their own separate variables so that we can, I don't know, multiply them and add them to the channels of the other pixel, and then get the result? And the way we do it is we use binary bitwise operators. Now the AND operator is what we can use to mask bits. Masking allows us to eliminate all of the bits that we don't want and just focus on the bits that we do want. Let me give you an example. Let's say we have an 8-bit number. 101 1010. And let's say that all we're interested in is the top nibble. We don't care about the lower nibble. No, let me rephrase that. All we're interested in is the lower nibble. We don't fucking care what the top nibble is. It's just in our way. We want to extract the lower nibble. What we could do is we could do something like this. We could create a mask which has ones in the part that we're interested in and zeros in the part that we want to mask out. And if we AND this by this number here will remain unchanged. Wait, that's a 0. Let me just do this again. This nibble is unchanged. Look, it was 1010, and after masking, it was still 1010. This nibble will be totally nullified. All zeros. It was masked out. And likewise, if we wanted the top nibble, we would mask like this. 0101 1010, and we would go 0000 1111, and masking like this 010. That gives us the top nibble. This mask gave us the bottom nibble. You see how that works? It's like fucking magic. So, by the way, writing this in hexadecimal, this would be, what would this be? This would be 4 plus 1 is 5. So this hexadecimal number would be 5, and this would be 8. This would be 5A. And we would be masking it with 0F. And the result would be 0A. That's hexadecimal. And the other one would be 5A masking with F0. And the result would be 50. That's how that works. And we can do that with our numbers up here. We could do it quite nicely. So let's say we wanted to extract the blue channel from this pixel, which is white. So we would go 00 F F F F F F 000000 F F, and the result is FF, which is just this value, and these ones are all nullified to zeros. Whew, I'm getting tired of talking now. And we could do the same, we could do the same thing if we wanted to extract the green channel. We'd put an FF here, we'd AND them together, and we'd get the green channel value. But there is one problem, and that is if we're extracting the blue channel, we'll get FF, which is 255, which is fine. The value of the blue channel is 255. But if we mask for the green channel, we're going to get FF00, which is 255 times 256. 1 second. There. So we go hexadecimal, FF00, in decimal. That's 65,280. That's not the value of the channel that we want. So what we have to do is after we mask this one out, we have to shift right by 8. And if we shift this right by 8 bits, the result will be just FF. So 000000. So we can extract any channel we want by first masking out the other channels and then shifting it back to the base position. So to get blue, we mask by FF. To get green, we mask by FF00 and then shift right by 8. Shift 1 byte to the right. And to mask for R, we we mask FF0000 and then we shift right 16 bits, 2 bytes to the right. And doing that, we can extract our 3 colors. But there's one more thing that I want to talk about. And then we're going to get to coding. Where's my thingamadoodle? So this situation here is if we take a bottom image and we blend it with a top image using a single alpha value. So in this case, alpha here would be alpha at 0.5, right? And here would be alpha at 0.9. See, if you look at my opacity here, 90%, 0.9, 0.5. This would be alpha is like 0.1, etc. But it's the same alpha everywhere. But usually in games, we don't want the same alpha everywhere. We want something called per pixel alpha. And we can get that. Like, look at this image right here. Not what I wanted. Control Z. This image here. You can see that this area here is opaque. You can't see through it. But this area here is translucent. You can see through it a bit. And this area here is transparent. You can see completely through this area. So how this works is, instead of having one single alpha value that the whole image is blended with, every single pixel carries its own alpha channel, and that channel is used to blend that pixel with whatever's below that pixel. And that works out very nicely, because if you look at our D3D color in the 32-bit value here, RGB, we have RGB, but we have this top byte that's just sitting around unused in XRGB. That's just a wasted space. So what we can do is we can use this value here, and we can use it as an alpha value. So if we say that this is FF, that corresponds to 1.0, or full opacity, full alpha, which means just cover up whatever's below this pixel. Whereas 00 means full transparency. Don't draw this pixel, only take what's below. And the middle ground, which would be either 8.0 or 7F, that would be about 50-50. So 0.5 alpha would be 8.0 hexadecimal. So we take this top byte and we say this is the alpha channel. And it's used to determine how much of we take from the source when we're blending with the destination. Okay, so we use bitwise operators to extract these values into separate channels. Then we calculate, we blend the channels together, and then we take the results and we pack them back into a 32-bit D3D color. Whew, that's the procedure. Now, let's see if we can't get it working. Alright, here's what I'm going to get you guys to do. I'm going to get you to open the font program that we were working on before. I forget which lesson that was, like 22 or 21 or something. Anyways, I'm going to make it a download on the website, so if you deleted yours or if you're not up to date, you can still get it on the forums. But go to your font project, open that mother up, and let's see where we're at. Game. Right. So this is the font program where we had dynamic memory allocation built into it, and we had our dudes just kind of walking along here. Good times, good times. Background, love this picture, love it. Okay, and what we want to do is we want to add alpha blending I want to be able to blend. Where is it? This one. We're gonna load this image and blend it onto the scene that we have there. So we're gonna have to add a new sprite drawing function, and we're also gonna have to add a new sprite loading function because first of all, bitmaps. Where's my load? Where's my bitmap shittle? Yeah, here we go. Bitmaps, they don't have very good support for alpha channels. So you can have a 24 or 32-bit bitmap with alpha, but it's not really supported well by all software, and it's hard to get Photoshop to save a bitmap with alpha. So generally, when we're using alpha, we don't use bitmaps. We use PNGs, and PNGs they're hard to load on your own. Like just using what is it? Just using SStudio, like fopen and fread and shit. It's pretty hard to load them because they're compressed, and there's a lot of math and algorithms involved with that shit. So what we're going to do is we're going to do what we should have done to begin with, and that is we're going to use a library to load our PNG file. This, what is it? This alpha image here, that's a PNG. See, alpha-half.png. We can even see here the pixel type, pixel format A8R8G8B8. So 8 bits per channel for ARGB. So we're gonna create a new loading function that's gonna load a sprite, and it's gonna load a sprite with an alpha channel, and then we're gonna blend that. We're gonna alpha blend that mother onto the scene. So first thing is first. All right, so here's the deal. I actually, from a different project, I already have code that will load a sprite with alpha. It'll load a PNG onto a surface, and it'll load the alpha data. But I don't want to explain a lot of this stuff right now, so I'm just going to go over it very quickly. I'm going to copy and paste it, and then I'm going to go over it. So go to your D3D graphics, and you're going to have to type this stuff in here, but I'm going to explain it along. So we're going to create a new function. It's called load sprite alpha. And it takes less parameters than load sprite because it's just awesome like that. It takes the pointer to the sprite structure that will be loaded, and it takes a constant a pointer to a constant character array. That's the file name. That's the string, right? And it also takes the D3D color key, although I don't think I use the key anywhere. Could probably lose the key, but I still put it in the sprite anyways. So that's not important. What is important is the file name and the sprite, the pointer to the sprite. Now, the thing we're going to be using for this, what do you call it? This algorithm here, this routine. It's a routine. Is GDI+. It's a library that's built into Windows, and it's used for a lot of Windows graphics stuff. It's an alternative to DirectX. Not as fast, but it's okay, I guess, if you're into that kind of thing. But it has a very nice class for loading up bitmaps in various file formats. So the first thing we need to do is, if we want to use GDI+, we have to include its include file. And the include file is not that one, this one, include GDI plus.h. So you're going to want to type that mother into here. I'll type her into here. And we also have to add the library to our project. We have to import the library. Now we could do that by changing our project settings. Oh, fucker. Control Z. There. Save that. We could do that by changing our project settings, but we could also import the library with this pragma comment library. This is actually a better way of importing libraries. I should have done this for everything in the... Fucker! There it is. It's just slow. So you have to add this comment here to add the GDI plus library. And this will allow us to link to this library after we've compiled our project. So you add these two things, and that should let us use GDI plus in our project here. Now, when we're using GDI plus, the first thing we have to do is we have to call GDI plus startup, and that will initialize GDI plus. So we create these two variables, and then we start up GDI plus using this function call. And after we've called this function, then we can use GDI plus as much as we want. Ideally, you shouldn't be calling this, you should only call this once in your whole program. But we're going to call it every time we load a sprite, just because I don't want to call it somewhere else. It's just a pain in the ass. So I'm calling it every time we load a sprite, but really we should only call it once in the whole program. Just a heads up to you guys. Then we create a GDI plus bitmap object, an instance of the bitmap class, and we call its constructor with this string, which is the file name, alpha-half.png. Now we have to put an L in front of this because the bitmap class prefers wide characters. So it prefers 16-bit characters. So we have to put an L in front of the string to specify that these are wide characters. Otherwise it'll use 8-bit characters, and the bitmap class won't like that. So prefix your string with an L to make it wide character string, which is what we do here. And we also create a pixel object, an instance of the color class. Then, as usual, we load our sprite structure with its data. And the height and the width, we don't pass height and width to this function. Like in load sprite, we pass it the height and the width. But in this one, we don't pass it the height and the width because we actually read that from the file. So we read the width and height of the bitmap itself, and we load the sprite accordingly. So it's automatic. And here, we have to allocate the memory for the surface. Now, this is not what we're going to use. We're just going to use normal malloc. I was using aligned malloc because that was doing something. I was doing SSE stuff. Don't worry about it. I'm just mumbling now. Don't think about it. So we'd use malloc to allocate some memory for our surface. So the size of a pixel times the height of the image times the width of the image gives us the size of the surface that we need. Then we loop through our the height of our bitmap and width of our bitmap, and we get a pixel. So we remember this pixel value. We pass a pointer to that structure, or is it a structure? It's a class. We pass a pointer to this instance of the color class, our pixel. We pass a pointer to the pixel, and we call getPixel with the x and y coordinates of the pixel that we want to get from our bitmap. And once we've got our pixel, we move it into our surface array. This is just our normal two-dimensional array addressing. and we use D3D color macro, but this time we don't use XRGB, we use ARGB because we have an alpha channel. And then we pass it the pixel.getAlpha, get red, get green, and get blue. And this will fill up our surface with the pixel data from our bitmap. So I hope that's fairly clear now. And this is how we can use GDI Plus to load up an image. It's very nice. It's not nearly as fast as our the algorithm that we made ourselves, but it has the advantage of being much simpler because PNGs are way fucking harder to load than bitmaps, and much less error prone because this code has been all written and tested, and it should be gold. So now we have load sprite alpha. Now, what else? Free sprite will work the same whether it's normal load sprite or load sprite alpha, because they both use malloc. So we can call free sprite on either of these, which is nice. So now we have the ability to load an alpha sprite from an image. Oh, I shouldn't. My bitmap. I'm hard coding my bitmap as alpha half.png. That's right, because this constant car is this is an 8-bit character string, but we need 16-bit characters, wide character string. So yeah, this won't work. We don't actually need this thing here. This is just a test, so we're hard coding the image that we're going to be loading. This function will only be able to load this image here, but it's fine for just for our testing purposes. We don't even need this color key either. I'm going to get rid of that, and I'm going to set the sprite pointer to key. I'm going to set that just to, I don't know, OX, 00, 01, 03, 01, F3. Just some random value for the color key. It doesn't matter. The main thing is that we've loaded our image here with alpha onto our sprite. Now that we can load a sprite, let me just build this to make sure that I haven't messed something up. Yeah, it succeeded. So this code will at least build. It shouldn't have any bugs in it because I've already used it in another project. Now we have to be able to draw this to the back buffer with alpha. So let's go to our d3dgraphics.cpp. That's this one. Now, as I shown you before, to blend you need the source pixel, which is the pixel from our sprite, but you also need the destination pixel, which is the pixel which currently occupies our back buffer. So in order to do this, we need a getPixel function which will retrieve the pixel currently in the back buffer. So we need to add a getPixel function to our D3D graphics. First of all, let's add load sprite to our H file, load sprite alpha. So we'll go d3dgraphics.h, and where's our load string? Load sprite. That's what it is. Load sprite. So we'll go void load sprite alpha. Build. Good. Now we're going to add another. We're going to add a function to our graphics D3D graphics class here. Where's getPixel? Put pixel. And we don't want void, we want D3D color because this function returns a value. GetPixel int x int y. So this one returns a value. And I'm going to copy that. Go to d3dgraphics.cpp. Let's find our putPixel function. put pixel. Let's add a get pixel here. And don't forget to add the... What the fuck? That was weird. Something's happening here. I don't know what it is. Stop! How do I stop this effects thing from going? Cursor effects, screen draw. Fucking dude, I don't want to do this shit. Tools, effects, annotation, cursor, hide cursor, fucker. Wait a second, I'm gonna pause. Okay. No, I still got this fucking thing. Gee, boss, how do I stop this bullshit? Alright, I figured it out. That weird thing let me... There's like some weird function that lets me draw on the screen, and I don't want to do that. Want to see how it works? Look at this. I'm drawing on the screen. What the fuck? This one? Yeah, I'm drawing on the screen. Now stop it, you bastard. Okay. What was I talking about? I think I was saying I had to do the scope resolution here. Graphics. There we go. Get pixel. So put pixel. We took a D3D color and we moved it onto the back rect. Oh, by the way, see this thing here? This is actually dividing by 4. This takes this pitch value and divides it by 4. And I don't know why, but I used shift because I thought, hey, I can use shift here. I probably should have just made it a normal divide. But anyways, so we're going to copy these asserts because they're good. And we're going to do a return. I'm just going to copy this. So yeah, that's why I do this shift here. It's the same as divide by 4. And I'll explain this when I go over the framework. But for now, all we need to know is that here we're moving C onto the back buffer, and here we're just taking the value of the back buffer and returning it at XY. The value of the back buffer at XY. All right. So now we have our get pixel function. Build. So far, so good. Now we need a function called draw sprite alpha. Load sprite alpha. Free sprite. Load font. Where's my draw sprite? Where's my fucking draw sprite, brah? Draw circle. Draw sprite. Alright, now we want draw sprite alpha. ALPHA, and it'll be the same parameters, nothing changes there. And again, we want to loop through our entire sprite, so that doesn't change either. What changes is the stuff inside here. Right? We're not going to use a key, a color key, so that's one thing that's different. We could use a color key with alpha blending. You can use them together, but we're not going to do that. We're just going to use pure alpha blending. So the first thing we do is we load the source color. That's the color on our sprite. And then I'm going to make it constant too because we don't ever change this value. I'm going to load a constant D3D color. Making it constant just means that we can't change it once it's been loaded. It's set in stone. It doesn't matter if you do it or not. Destination, alright. So source is equal to our surface. Destination is equal to get pixel at what? Shit. Well, it looks like getPixel is already a function somewhere else. That's bullshit. But we can specify that we want D3D graphics getPixel by calling this pointer fucking dick smack getPixel. Why is this not working? I bet you it's because this is not. 1 second. This has to be declared. No, yes. Draw sprite alpha. If I put this here, void. Now I go over here. Now let's try get pixel. Get pixel. It should prefer the local one. Right. Now we have our get pixel. There's also a global function getPixel, apparently, but we don't worry about that. We're going to call the getPixel for D3D graphics, and we're going to call it with the X and Y value, and that will be our destination pixel. So we get our source pixel from our surface, we get our destination pixel from the back buffer. Now, we have to extract the channels. So load source and destination pixels. Extract channels. Constant. How should I do this? Alpha source is equal to, and here's what we're going to do. We're going to mask, first we're going to mask out all the other channels. So to get the alpha channel, we go 0, 0, 0, 0, 0, 0. 1, 2, 3, 4, 5, 6. One too many zeros. So the very top byte is the alpha channel. So we take this mask and we go source and this mask. I'm going to go like this. Alpha, I'm going to go src alpha. Source alpha is equal to source and the alpha mask. And then we have to shift that right by 24 bits. And that will shift this one into the base position. And then we go constant source red is equal to source and OX 00 FF 0000. And we want to shift this one right by 16 bits. And we're going to do this for all the source and all the destination. So I'm going to pause it. Alright, so I've created all my source and my destination channels here by your basic masking and shifting. So now I have my source alpha and blah 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 blah. Now here's the deal. Here's the problem here. In our math, we basically took the channels and we multiplied them by an alpha value, but our alpha value was a floating point value between 1.0 and 0.0. However, our alpha channel is not floating point. It's just in your normal binary integer from 0 to 255. Oh shit. I said constant, but I didn't specify the type of data. This is a constant unsigned car. Wait a second. Alright. So yeah, we'll load up all of our channels here. But the problem, like I was saying, is that alpha here is not a floating point value. It's a it's an integer, right? So we won't, if we multiply, for example, if we take our red channel source and we multiply it by our alpha channel, and let's say that's 128, and then we add it to our red destination. This bugger's in the way. Get out of my way. Destination times 1 minus 128, right? 1 minus alpha. We're going to get like a fucked up weird ass result. We're going to get negative here. We're going to subtract this one from this one, basically. This times 128 minus this times 127. And they might cancel each other out or whatever. It's not what we want, right? So how do we solve this problem? Well, it's quite simple. The value 255 corresponds to 1.0 alpha, and the value 0 corresponds to 0 alpha. So here's what we're going to do. Let me just erase some spots here. We're not going to convert the alpha to a floating point value. We could do that, but that would be wasteful. It would take a lot of time to convert and then multiply and then reconvert back to integers. So what we're going to do is we're going to go, for example, in the red channel, we're going to go red result is equal to red source times alpha divided by 255 plus red destination times 1, wait, fucker. Go away. 255 minus alpha divided by 255. Now what this will do is alpha divided by 255. If alpha is equal to 255, 255 divided by 255 is 1. So this will be multiplying by 1. If alpha is 0, 0 divided by 255 is 0, multiplied by 0. And if it's, for example, 128, 128 divided by 255 is about 0.5. So we get the same effect, but we're not using floating point values. We're only using integers. And we can actually factor out this 255, and we can do this. Rs times alpha plus Rd times 255 minus alpha. 255 is 1, right? So 1 minus alpha. And then we can take this whole thing and divide the result by 255. And that will get us our normalized R result. And that's how we do it all in integers without having to convert to floating point values first. So how do we do this? We go constant unsigned car result red is equal to source red times source alpha plus destination red times 255 minus source alpha, and we take this whole damn thing. Where's my end? There it is. And we divide it by 255. Now you might think that in these calculations the values might overflow. Like for example, if this is a 8-bit value and we have source of 255 and we multiply by 255, that will overflow. But in C++, these will automatically be promoted to probably a 32-bit value, so we'll have plenty of room for the bits to I don't know, roam, I guess, whatever. So you don't have to worry about overflows if you were thinking about that at all. So it'll multiply by the alpha, multiply by the inverse alpha, and then divide by 255 to normalize it all in the end. And I'm going to do this again. Alright, so now we have our result red, green, and blue values that were calculated using our source and destinations. Destination alpha is not used. I was just copy and pasting, and I copied that one too. So that's obviously not important. The only alpha that we're interested in is the alpha of the source, because that's the thing that's going to be blended over top of whatever is sitting below it. So there we go. We blend our source and our destination to get a result. And the final thing we want to do, so we have extract channels, blend channels, and the final thing we want to do is we want to pack the channels into our pixel. So pack channels back into pixel. And how we do that is we call put pixel, and we do it with our X and our Y, and our color is just D3D color underscore X RGB. Obviously alpha is not important. Alpha is only used for blending the source and the destination, but once we have the final blended value, we just slam it down back into the back buffer. So we go result red, result green, and result blue, and that packs the channels back into a pixel and fires pixel onto back buffer. And here we go. We load our pixels, we unpack the channels, extract them into separate variables, blend the channels together, and then pack them back into a single pixel and put them back on the back buffer. And that, my friends, is how you do alpha blending. Build. Now there are a number of optimizations we can do, but we won't worry about it right now. And let me just tell you right now, this will probably be slow. So don't expect to be able to do this routine with a lot of sprites. But that being said, we will be able to make it much faster in the future by doing some simple optimization. But for now, we won't worry about the optimization. I just want to give you the basic theory. But if you try to run this and you're like, wow, that's so slow, this sucks balls, just remember that the optimization is coming. So don't lose hope. Okay, so now we have our draw sprite alpha function. We have our load sprite alpha. So let's create a sprite, load it, and draw it. So we go to our game.h. Actually, it's getting kind of late, so I'm gonna stop the video here, and when I come back, we're gonna load up. We're gonna draw that alpha. We're gonna test out our alpha routines, and then I'm gonna wrap up by showing you one more thing we can do with bit twiddling, and that'll be the end of the lesson. So when I come back, which will be only about 1 second for you guys, we're gonna try this alpha blending shit out. See you on the other side. Alright people, let's put these routines to the test. So we're going to implement where I say we're going to load a sprite and we're going to draw it on the screen. So we got to go to game.h and we've got to add a sprite structure to our game class. So we'll go sprite alpha sprite, and then we'll go to game. We're gonna load that mother. So load what the fuck, god damn it, again I continue to fail at typing. Sprite alpha. Okay, was it alpha sprite? And we get the address of our alpha sprite. Who doesn't love Sprite? Gotta get me some of that high fructose corn syrup. Good stuff. And when we die, we've got to free our sprite. So we'll go free sprite, alpha sprite. And last but not least, we've got to draw that mother. So we will draw our alpha sprite last of all of our demo objects, but we'll draw the text over top of the alpha sprite. So oh, one second, I think I forgot something. Alright, yeah, so we'll do graphics dot draw sprite alpha, and we'll just draw it at 0, 0 for now, and we'll give the address of our alpha sprite. And that should be that, except that it's not that, because actually I recorded all of this shit before, and then Camtasia decided to be a total bag of dicks, and it didn't record any of the audio. But that's okay, because I fucked a bunch of shit up, and I'm not going to fuck that shit up this time. So, what you need to do is you need to go to your, let me think here. You need to go to your folder here, and you have to actually copy. You got to copy the alpha into here, otherwise it won't fucking work, obviously. And that wasted about like 3 or 5 minutes in the last time I recorded all this shit. So at least that's a good thing about Camtasia screwing me over. It had my best interests at heart, I guess. Now if we load this, we should get yes. And yeah, it's bloody hella slow. But that's just that's the name of the game. So if you've got a super slow ass demo going here, then basically you've got the exact same thing that I've got. Let's see exactly what our render time is for a single frame, just out of curiosity. It's still, there we go. We're getting about half a second per frame. That's pretty damn slow. 2 frames a second is what we're getting. That is piss poor, but that's pretty much, I don't know, par for the course, I guess. The reason why it's so slow is because, I think I said this before, but writing to video memory is slow, but reading from video memory is way slower than writing. So, and you might be asking yourself, does that mean we can't do alpha blending? I mean, that's obviously too fucking slow to be practical. Well, there is a trick that we can use. I don't know if you'd call it a trick, but a technique that will make it about 100 times faster. And I'll be showing you guys that later on. So for now, alpha blending is too slow for us, but we're going to make it a hell of a lot faster, so wait for that. Now, one thing that kind of messes me up, let me just show you guys this. If we go to debug and we build it again, it's going way faster in debug. Now that makes absolutely no fucking sense. I have no idea why that would be true. This totally just, like, look at this. It's over twice as, it's like 3 times as fast in debug mode as it is in release mode. And like, that's the opposite of what it should be. And I'm sorry guys, I have no answer for why this is. The good news is it doesn't really matter, because because like I said before, we're gonna introduce an optimization later on that will make it like 100 times faster. It'll be plausible to have large alpha blended sprites and still run the game. So yeah, but as you can see, it works. That's the main thing. It works. It's transparent. The frame is drawn properly. It's just slow as balls. So now there's one last thing. I made a little mistake. Number 2 here was when I made my thing here. I'm not taking into account X offset and Y offset. So if I go in my game and I say I want to draw this sprite at 200, 200, I think you can guess what's going to happen, right? What changes? Absolutely fucking nothing, because I'm not taking into account the offset values. So that's simple. We just go copy this. We don't change them in here. We'd only change them when we're accessing the surface, the background surface. So we go this X plus X offset and Y plus Y offset. And if I just copy this, I can paste it into here. And now if I build this mother, now we got it over here and everything's fine. So again, the slowness is expected. There's nothing that we can do about that right now, but trust me, it's very this problem is very tractable. We can handle this no problem. However, the fact that debug is faster than release, that blows my mind still. I don't really understand why that is the case. Maybe I'll look into it later if I have some time, but I don't know if there are any gurus watching this video for shits and giggles. I would be interested in knowing why you think that might be the case. But anyways, it's not a big deal because we'll be doing something different with this later on. But that is how you do alpha blending, and that is one application of this kind of bit banging. And that's not bit banging, it's called bit twiddling. Now one last thing I wanted to tell you is this D3D color XRGB, this macro. If you look at it, if you actually go to the definition, you'll see that D3D XRGB is just ARGB with FF and then RGB. So if we go to D3D color ARGB, look what you got here. You've got a bunch of bit shifting and anding and bit ORing, bitwise OR, bitwise AND. So this thing that we've been using, this XRGB, which is actually just ARGB with the alpha set to FF, it's all just bit twiddling. So that's how that is actually done. It's just a bunch of bit twiddling. And we could do that ourselves too, but why when we've got this nice macro here to do it for us? So that's just another little a little thing for you to look at about bitwise operators. Now, last thing we're going to do before I call this a video is I'm going to show you guys one more application of bit twiddling. And this application is actually very important to Direct 3D. And this is the reason why I'm showing it to you now. Because when we look at the framework, we're going to be seeing this application. So what I'm going to get you guys to do is create a new console application. You don't have to create one. You can just watch me for this. You don't have to follow along. But you can if you want. It's all good. It's all good. We're going to create console application, empty project, finish that mother. And we're going to add, what are we going to add? A CPP file. You know the drill. Get our main on. And we're going to include stdio.h. We're going to get our void main. People say that void main is bad and evil, but whatever, it fucking works, I don't care. technically it's supposed to be like int main, and then you're supposed to have something in here that, like, I don't know, some arguments, but fuck it, who cares? The thing we're going to do in this little application is we're going to create a data type that's going to hold the results of a test. So there'll be many items in the test. So we're going to go struct test results. It's an STD test. So you got a bunch of STDs and you're just checking whether they're positive or not. So one way we could do this is we could create a structure and we could have a bunch of Boolean values. For example, bool has herpes. Bool has syphilis. I don't know if you're spelling that right. Bool has gonorrhea. And bool has, what's another one? Chlamydia. Chlamydia? I don't know. I can't spell worth shit. Okay. So you have this structure and it has a bunch of Boolean values, and then you could create a function which would print out the test results. So we would go void print results, and we would pass it a test results structure. Results. We're going to pass the structure by value, not by pointer. Do you know the difference between passing by value and passing by pointer? If not, you can post in the forum and maybe I'll answer the question. Or maybe I'll just laugh at you. No, I'll probably answer the question. Anyways, we're passing this by value, and what we're going to do is we're going to check every results dot has chlamydia. So we're going to check if we have chlamydia. And if we do, then we're going to print F. You have chlamydia! Exclamation mark. Am I even spelling it the same? I think I am. Let's put a control N on the end of that for fun. So like that, and we're going to do the same thing for every little disease there that we're testing for. So wait a sec. Alright, so now I've got this all set up nice and whatever. So I've got my structure that will hold the test results, and I've got my function that will print out the test results. And then I can do stuff like that. So I can get some test results. We'll go test results, and we'll say results dot has chlamydia, fucker, has chlamydia, yes, space, is equal to true. So we have chlamydia, and results dot has herpes is equal to true, and results dot has syphilis is equal to false, and results dot has gonorrhea is equal to false. So we got herpes and chlamydia. It's not the best news, but whatever. And we can do we'll just do print results, and we'll pass it the results. And build. Success. And if we do it, you have herpes, you have chlamydia, right? That's what we expect. Now that's one way we could do this. Now let me just show you one thing. If my Visual Studio Express will stop freezing up on me and being a dick, like it's always being a dick. Why are you always doing this to me? Okay, thank you very much. So let's do a little test here. Printf test results struct occupies %, no, %, no, %, fuck, where is it? There it is. D bytes in memory. Bop, blap, blippity. And we'll go size of test results. So Let's just do a little test here, see how much space this occupies in memory. So test results struct occupies 4 bytes in memory. Now this makes sense because, again, things frozen up on me. Wait, I fucking hate that. Anyways, because the structure has 4 bool variables, and every bool takes up 1 byte in memory. Now, let's say we had to store 1 billion different test results for 1 billion dirty people. That would be 4 billion bytes, right? It's a lot of space. But think about a Boolean value. Do you really need 8 bits to store a true or false? A true or false is the same as a high or low, 1 or 0. You think you could probably store that all in 1 bit. So to store these 4 values, we should only need 4 bits. So I'm going to show you guys how to store this in just 4 bits. All we got to do, first let's change this here. We're not going to use test result structure. We're going to use an unsigned, actually fuck unsigned, we're just going to use a car. Doesn't matter if it's unsigned or not, it's not a big deal. Alright, so we're going to store these 4 flags here, or these 4 test result items, in a single car, a single 8-bit value. Now how do we do that? Well, what we do is, let's get rid of this because we're not going to use it anymore. We're going to go #define, and we're going to go how shall I do this? We'll just go herp is equal to 1. Define sif is equal to 2. Define fucking bullshit. Define gone 4. Define clap. Clap is, oh, what can you guess what it is? 8. All right. So first we make these 4 defines here. We can use other things besides define, but we're just going to use define for now because that's what DirectX uses. And here, how do we test for results? How do we test if we have herpes? We go herp and results. And I'm just going to copy this. Copy paste. Copy paste. And copy paste. Here we go. And now, copy that one. Replace herp with sif. Replace herp with gone. Replace herp with the clap. Okay, so far so good. So we do a bitwise AND between our results character and our herp value or our sif value. And now, how do we create our test results data here? We go car results is equal to, well, let's say we wanted to have herpes, syphilis, and the clap. We got the trifecta here. We go herp or bitwise or, fucker, that's not a bitwise or, sif or clap, and let's print results here. And just for fun, we're just going to get the size of car. The test results, we'll just go the result car occupies whatever bytes in memory. Okay, let's hope that this doesn't fail. Succeeded. So you have herpes, you have syphilis, and you have chlamydia. Results car occupies 1 byte in memory. So we went from 4 bytes to just 1 byte. So if we had to store 1 billion people's dirty test results, that means that we could store them in using 1 gigabyte instead of 3 gigabytes. And that, my friends, is a big savings. But how does it all work? And why do we choose these numbers? Can you think of it? Well, as you might expect, I'm going to tell you because I'm a nice guy. That's the kind of guy I am. I'm just going to get myself a new layer here. All right. So, herp. There's an R in there somewhere. Let me just get the order here because I forgot it already. I've got a mind like a sieve. There we go. Herp, sif, gon, clap. There you go. Herp, sif, gon, clap, which is OX01, OX02, OX04, and OX08. These are just our normal 1, 2, 4, 8 because we haven't gotten to over 10 yet, so the hexadecimal magic doesn't kick in yet. But anyways, the numbers 1, 2, 4, and 8, what do they look like in binary? Try to write them out by yourself. Here's 2, here's 4, and here is 8. See a pattern emerging here? So for every disease here, every disease result has its own bit. So the first bit here represents herpes. The second bit represents syphilis. The third bit represents gonorrhea, and the fourth bit represents the clap. So, what happens if you want to create a test results where the person has the herpes and the clap? Well, we take the herpes, 1, we take the clap value, and we OR them together. That's my new symbol for ORing, logical OR, bitwise OR. And if you know how OR works, you know that as long as one of them, at least one of them is a 1, the result is a 1. So here they're both 0, so the result is a 0. Here 1. So you basically are combining all the 1s here. And this is the result, which has the herpes bit on and the clap bit. Now, if you want to later on test to see if you have herpes or the clap or syphilis, you would go, for example, if you wanted to test for herpes, you would take this result here. This is the test results. And you would take the herpes value, and you would do a bitwise AND. And that would, well, bitwise ANDing this is 0, right? 0, 0, and this one is a 1. And because it's a non-zero, that means it's true, right? Let's try to test the same value here for gonorrhea. So gonorrhea is 0, 1, 0, 0. So we'll go our test results, and we'll try to AND it with the gonorrhea value. Here's our AND. And so we have 1 bitwise AND with 0 is 0. 0, this one is 0, this one is 0. Result is 0, meaning false. Non-zero, meaning true. In an if statement, right? If non-zero, do code block, whatever. So that's how you do it. You use OR to combine these different bit flags. These are called bit flags. At least I think that's what they're called. That's what I'm going to call them, bit flags. You use the logical OR to combine bit flags, to mash them together, and then you use the logical AND to mask out all the ones you don't care about and just test a single bit flag. Does that make sense? I hope that makes sense, because it's not that difficult. And the thing is, my friends, Romans, and what the other thing was, I forget. Where is it? if we look at the framework, that thing that I'm going to teach you in about 2 lessons, or in 1 lesson, depending on how you count. Let's look at the framework here. Let's look at the D3D graphics here. And we're going to look at, where's my graphics chisel? Here we go. Look at this thing here, for example. Create device. So we have a bunch of, we're creating the object that represents our graphics adapter. So we give an adapter identifier, and here we're just saying give us the default adapter. And then here we give us a device type, and the device type is HAL, hardware abstraction layer. You don't have to worry about this shit. Now, give us the window to, give us the handle to the window, just hwind. And here we're saying give us the flags of the behavior of the device. And we're combining 2 behavior flags. We say we want hardware vertex processing, and we want a pure device. And we use a bitwise OR to combine these 2 flags. This flag here, as you can see down there, I can't point to it, but you can see the number there. It's 0x000040, and that's a single bit. And this one here is a 10. That's another single bit. So these are just flags that represent behavior for the device. And this kind of shit happens other places. Here there's a flag, but there's only 1 flag, so we're not using any bitwise OR. And in Windows, let me just look here. I think there are some of those things too, but I'm not using them here, so you can't see them. But yeah, those kind of bit flags, they're used throughout Windows and Windows 32 and throughout DirectX. So I wanted to show them to you guys, and I did show them, and it's all good. So I think I'm going to call it a video here. Hope you guys understand a little bit about bit flags and about bitwise operators in general. And I hope you guys got an idea about how alpha blending works. And hopefully, definitely we're going to make it faster in the future. So don't worry about that. Have faith. Our engine will be fast. But for now, we'll just be happy that it works. It's technically correct even if it's not efficient. And we'll work on that later. So if you have any questions, feel free to drop by the forum and ask, and I will answer them. Probably. Yeah, I think I will. And next lesson, look forward to all this stuff. And probably 1 more topic. And there'll be short little topic things that I'm going to go over. But I'm probably not going to have like a practical problem to demonstrate them. Like in this case, I demonstrated bitwise operators through the problem of alpha blending. I'm not going to do something like that. I'm just going to briefly introduce these concepts because I want to get to the framework. I just want to get it over with because people have been bothering me about that since like the 2nd video I created, and just want to finally show you guys because it's not that complicated. Trust me, it's going to be easy. I just don't want to have to stop every 5 or 10 minutes to explain this shit. I want to be able to move smoothly through the framework and explain it in a straightforward fashion. So, next lesson, we're going to learn about references, constant correctness, pointers to functions, and global variables and static global variables. So look forward to that, and keep your stick on the ice. And see you in the forums. Later.